In this video, we're discussing learning outcome number 3 for lesson 4.4, which is all about understanding the difference between permutations and combinations. And then we're going to learn the permutation rule for counting permutations, and we'll hopefully understand where that rule comes from. So if you're trying to decide between permutations and combinations, what you're really asking yourself is, does order matter here? Both of them are arrangements of items, but with permutations, order matters, and with combination, order does not matter. So with permutations, we're dealing with, or we're thinking about, arrangements of items in which different sequences of the same items are counted separately. So let's say you have the letters A, B, and C. If I have A, B, and C, I could arrange them as A, B, then C, or I could have A first and then C and then B, or I could have B first and then A and then C, or B first and then C and then A, or C first and then A and then B, or C first and then B and then A. All of those would be counted separately as 6 different permutations because they have the same letters, but they're all in different orders. Now, if I was looking at these same letters and I was counting all of those as the same, we would call that a combination. Combinations are arrangements in which different sequences of the same items are counted as the same. So they're all the same combination because they all contain the letters A, B, and C. Here, order doesn't matter. We've got a great mnemonic for permutations and combinations. When you're thinking of permutations, think permutations position, because with permutations, positions make a difference. So one example that I can think of for permutations is medalists at the Olympics. If we have these 3 gymnasts and they are our top 3, it does matter who gets the gold, who gets the silver, and who gets the bronze. So that's a permutation. Now, combinations can be associated with committees. You know that when you're talking about members of a committee, it really doesn't matter who you picked first to go on the committee or who you picked last. If you rearrange those members, the rearrangement doesn't matter. They're going to end up in this exact same committee. So if I have these 6 people and then I just put them in different seats, it wouldn't matter if I was just interested in the 6 people in that group. So that is a combination. So think combinations are associated with committees, as rearrangements are that result in the same committee, and permutations are associated with position. If you change the position, you've got a different permutation. So here's our permutations rule. If you want to count permutations, you'll use this rule. So it says, when n different items are available and r of them are selected without replacement, the number of different permutations is given by this notation with this formula. So we have n of them, and we're choosing r of them, and we want the number of permutations where order matters. In order to find that, you take n factorial and you divide by n minus r factorial. This is actually just modified from the multiplication counting rule and the factorial counting rule that we've discussed in earlier videos. You'll see when we look at an intuitive example. So here's our first example, actually our only example in this video. It says, in a horse race, a trifecta bet is won by correctly selecting horses that finish first, second, and third, and you must select them in the correct order. Then it says, the 140th running of the Kentucky Derby had a field of 19 horses. In part A, we're asked, how many different trifecta bets are possible? So when you're placing a trifecta bet, you are selecting which horse you think will be first, and then you're selecting which horse you think will be second, and you're selecting which horse you think will be third, out of a field of 19 horses during that particular running of the Kentucky Derby. Well, let's take the intuitive approach first. In order to take the intuitive approach, we're just going to modify that modification counting rule and the factorial rule. Just think it through. How many choices do you have for that first horse, for that first place horse? Well, if there are 19 horses, you've got 19 choices. Then how many choices do you have for the second horse? Well, if you've already put one in first place, well, you have 18 choices for the second place horse. And then for the third place horse, since you already took 2 of them away for first and second place, you've got 17 choices left. So we have 19 times 18 times 17. If we multiply those together, it turns out we get 5,814 bets. That's the intuitive approach. Now, it turns out that that formula for permutations gives you exactly the same result. So if we have n, or if we have 19 horses, that's our n. There are 19 horses available. And we're selecting R of them, and we're not putting them back in, so that we're selecting them without replacement. Because a horse can't simultaneously be first place and third place, a horse can't simultaneously be first and second, and so on. Then the number of different arrangements is found using the formula. So we have 19, and we're choosing 3 of them, and order matters. So according to the formula, we've got 19 factorial, that's our n factorial, over 19 minus 3 factorial, that's n, the number that we have to choose from, minus the number that we're selecting factorial. Now, if you expand that 19 factorial, you see it's 19 times 18 times 17 times 16 times 15 times 14, all the way down. So it's really 19 times 18 times 17 times 16 factorial, because 16 times 15 times 14 all the way down, that can be summarized as 16 factorial. And that 19 minus 3 factorial in the denominator, that's another 16 factorial. So those 16 factorials cancel, and you're just left with that 19 times 18 times 17, which is exactly what we got when we took the intuitive approach. We said we've got 19 options for the first place horse, 18 options for the second place horse, and 17 options for the third place horse. You multiply those together, and you get this 5,814. Now, I would love it if you always took the intuitive approach to getting these answers. But if you aren't comfortable with the intuitive approach, if you'd rather use a formula, you can just say, okay, I'm talking about first, second, and third place. Order matters. Therefore, it's a permutation. Therefore, I'm going to use my permutation formula. And you're going to have the permutation formula on that formulas and tables sheet during your exam. So you can rely on that if you want to. But I would prefer if you can just try to learn the intuitive approach, then it'll make more sense and it won't be just blindly applying a formula. Now, part B of this question says, if a bettor randomly selects 3 of those horses for the trifecta bet, what's the probability of winning by selecting California Chrome to win, Commanding Curve to finish second, and Danza to finish third, as they did? Well, it looks like there's only one way to choose Chrome to win, Commanding Curve to finish second, and Danza to finish third, and we're asking for a probability of winning. And then the second part of part B says, do all the different possible trifecta bets have the same chance of winning? Ignore the deadheads win, or ignore deadheads, excuse me, in which horses tie for a win. Okay. So here's our answer. I've got that given selection with Chrome first and so on. The probability of getting that given selection winning is the number of ways to select those horses in that order divided by the total number of possible arrangements. Now, we already found the total number of possible arrangements when we found the permutation in part A. So it's just, there's only one way to select them in that order, and then we're dividing by that 5,814 that we found in part A. Now, with regard to the second question, let's look at it again. Do all the different possible trifecta bets have the same chance of winning? They really don't. So we made an assumption when we calculated this probability that all of them had the same chance of winning. But the reality is that some horses are actually faster than others, and they have a track record of being faster than others. So they don't all have the chance of winning. So this probability may not be accurate in the sense that it's not necessarily the probability of winning. It's the probability of randomly choosing one selection of horses in a certain order out of the possible orders or out of the possible arrangements of those 19 horses for that first, second, and third place, if that makes sense. So since some horses are faster than others, like maybe this isn't a true probability of winning. And that's it. I will see you in the next video.